Welcome back. Last lecture, last video on Simplex method. And if we've done our job correctly, then everything is just going to come together during this last video, in the sense that now that we understand the primal simplex method and the dual simplex method both, right, we can combine both of those together to maximize or minimize almost any objective function in almost any combination. And today we'll see greater thans and less thans in the same situation, right? Theoretically, mathematically, there's still a lot going on behind the scenes. But by the time we're done, hopefully you'll be able to see this a lot more fluidly than we did in previous weeks. Let's remember that the primal simplex method, or the regular simplex method, only was able to deal with maximization problems. We had maximize z equals blank, and in that primal simplex method, we were only allowed to have less than or equal to inequalities. Right? Yes, we still had all the variables being positive. Right? You see, I haven't even written that part in my little example here. And then we got one solution. We found, right, where to pivot, right, the entering and exiting, such that we formed, right, a set of basic variables which matched up with the optimal solution. Remember, every basis, every set of basic variables and non-basic variables, each of them represented a corner point. And all we had to do was find the correct corner point, because we proved in the very, very first week we did this that only the corner points matter. It's only when we have two corner points giving us exactly the same, right, those co-optimal corner points, that we're allowed to also include the line in between the corner points. So we have the basic simplex method, or the primal simplex method. We then went on to find the dual simplex method. And the dual simplex method allowed us to minimize objective functions. So now instead of maximizing z, we were allowed to minimize z. But in the standard, or the most common scenario, the dual method only allowed greater than or equal to inequalities. And this was because, again, it's that flip side of the coin. And so everything had to be backwards, including the inequalities. But we found that it worked surprisingly similarly, right? Once we found that idea that minimization was maximization, right, but kind of upside down, we were able to use many of the same ideas and intuitions for the dual simplex method that we were for the regular simplex method. But today, now, right, we're going to solve problems that aren't standard maximization or standard minimization problems. That is, they've got some kind of mix between greater thans and less than. They might be maximized, they might be minimized. Right? How do we handle ourselves when we can't control every part of our puzzle, right? Every piece of our problem? This is what we'll call the extended simplex method. Right? I call it extended because it allows us to solve more than just the standard maximizing or the standard minimizing problem. Right? It basically boils down to 4 steps, and we've learned each of these steps before. We're just pulling them all into one process. And first, I have to ask myself, am I following the primal dual simplex method ideas, or am I following the dual simplex method ideas? We saw different types of pivoting, right, for each one. And so we have primal if we're maximizing, or dual if we're minimizing. Remember, primal was looking to get rid of those negatives in the bottom, right? And the dual method was actually looking to get rid of the negatives on the right side of the matrix. In number 2, right, I need to make sure that everything is less than or equal to. And remember that even in the dual simplex method, we still corrected our matrix so that we only had less than or equal tos. But if we have a greater than or equal to, we corrected it to less than or equal to, multiplying by -1. We did that as well. We used that same -1 trick when we did the dual minimization. We did that here as well. Then in step 3, or principle number 3, we ask, right, are we feasible? The primal simplex method always began at a feasible solution. Because if you remember, the primal method always started at 0, 0. And if you had less than or equal to's for all of your inequalities, 0, 0 was always a primal feasible solution. So that wasn't really an issue for the primal simplex method. But it was an issue for the dual simplex method. The dual simplex method began somewhere which was better than optimal, but it was not feasible, and we had to go through the process to find a feasible solution. We usually use dual pivots to fix solutions which were not feasible. We basically took one step back towards feasibility. And in principle number 4, we address the optimality conditions. The optimality conditions were a little bit different for the primal and the dual simplex method. Remember, in the primal simplex method, we wanted to increase the objective as much as possible. So we got rid of all of the negative numbers in the bottom row. But in the dual simplex method, we wanted to decrease the objective as much as possible. So we only wanted negative numbers in the bottom row. So it was a little bit different. And we used primal pivots whenever we had feasible solutions, but not optimal solutions. So we're basically sandwiching our objective function in between the minimum and the maximum. So we had to decrease the function in order to make it feasible. But then once it was feasible, we were allowed to optimize it using the standard or the primal simplex method. I know that sounds like a lot, but we're going to go over several examples today of showing all the different facets of the simplex method, both when we see the primal steps and when we see the dual steps kind of being combined a little bit. So let's take a look at several examples. The first one will be only a matrix example. So in this problem, I've already given you the matrix and I've already set it up for you. There's not a word problem here. In this problem, I see some negative numbers on the right side. Right? That tells me this probably was a greater than or equal to in the system of inequalities that came before. I see some negative numbers in the bottom. So I'm hoping this is a maximized problem. And I've put down here on the bottom that it is a maximized problem. If this were a minimized problem, it'd be a little bit different, right? But this is a maximized problem. But notice how in this matrix, when I first look at it, my basic variables are S1 and S2. S1 equals -10. S2 equals 25, right? So S1 equals -10, and S2 equals 25. And all of the other, I guess Z is always a basic variable. I never say that out loud, but it always is. Right now it's 0. X1 and X2 are non-basic variables right now, and so they are 0. But this particular set of basics and non-basics is not feasible. I can tell you it's not feasible because S1 is equal to -10. And that's not feasible. Remember, every time we had simplex, all of my S variables and all of my X variables, they must always be positive. Z was allowed to be negative if it had to be. We didn't see that too often. And so all the X's and S variables, they must be positive. And so that means this is a non-feasible solution. Right, so I'm in a maximized scenario, but yet I'm going to have to do a dual simplex method pivot, right? Because really, normally whenever we moved from non-feasible back towards feasible, that was usually part of the dual simplex method. So let's take a look at doing a dual pivot. The dual pivot asks what's the highest negative number on the right side. Here it's -10. There's only one negative number there. That tells me that the pivot which goes with it here is S1. So that tells me my exiting variable is S1. I'm about to get rid of that pivot, right? Because that one's causing me the most, right, out of line with feasibility. But to figure out which other pivot to bring in, I'm going to do the ratios. Right? The ratios in the dual pivots are the bottom row divided by the exiting row. So here, this pivot is -2 divided by -2. That's equal to 1. This pivot is -2 divided by -1, which is 2. I always pick the lowest positive ratio, which tells me this ratio wins, and my new pivot goes right here. And that tells me my entering variable is x2. So let me swap out this x2 for my s1. And to do that, I'm going to go to the computer, type this in, and I'll meet you back on the computer page. Okay, got it all typed into the computer. And if I remember correctly from the OneNote, my pivot is supposed to be right here in the x2 column, which will replace this pivot here in the s1 column. Let me get out my row operations to do this. So to make that -2 into a 1, I multiply times -1 over 2 times row 1. Do that operation. Then, to clear out all the numbers below it, to clear a positive 3, I need a -3 times row 1. To clear a -2, I need +2 row 1. Remember, on the computer, I have to list the row which is changing first. If I were writing this on a piece of paper, I would usually write -3R1 plus R2, for example. That's just a quirk of this computer program that I'm using. Do these operations. Now that these are done, I see that I've got a new pivot here in the x2 column, and I've replaced the one from the s1 column, so it's no longer there, and I've arrived at a new solution. Let's see, this solution is x1 equals 0, it's non-basic. x2 equals 5, that's fine. s1 equals 0, it's non-basic. s2 is equal to 10, which is also fine. And z equals 10. Now I'm at a second solution. This solution is feasible. I know it's feasible because all the numbers in the last column here, or at least these first two, they are positive. And so this solution is feasible. But let's see, is it optimal? Right? We're maximizing here, so I'm looking at primal simplex method. In the primal simplex method, if there are any negative numbers in the bottom, that means the z could be higher. So this is a feasible solution, but not an optimal solution. Let's move towards optimality. Normally, I would tell you to pick the biggest negative number in the bottom row, but here is a tie. I almost got rid of this problem because of the tie, but I think that we need to discuss what happens in terms of ties, because I don't think we've discussed it too much in the past. If there's a tie, you can choose either one, but when you make a bad choice, right, and there's no way to know for us, right, ahead of time what the quote-unquote bad choice is, if you make a bad choice, it is at least theoretically possible that you cycle around and you come back to the same solution and you keep going through the simplex method over and over again, and you'll never find the optimum solution. Okay? So the math nerds will call this cycling in the simplex method. And to prevent this kind of cycling, right, to break a tie, I'm always going to choose the first variable. Right? That means the left side, if I'm doing a regular pivot method, or a regular primal simplex method pivot. And I'm always going to choose the top variable, closer to the top, if I'm doing a dual simplex method, pivot. So I'm going to choose this -1 in the x1 column and look at the other ratios above it. See, this ratio is 5 divided by 0.5, so that ratio is equal to 10. And this ratio is 10 divided by -0.5, that's -20. You're not allowed to pivot on a negative ratio, so that gives me one choice and only one choice. Entering is x1. And exiting, see, here's my ratio. That means the pivot, which is going away, is the x2. Well, I'm sorry, x2. I know that you just came into my bases, right, because I just brought it in, but immediately it's going away in terms of this one. Now, if you were to look at this problem and say, you know what, Professor, I'm betting that really in a real solution, right, my s variables are going to be 0 and my x variables are not, and you wanted to pivot using the S1 column, you would be free to do that, right? Just be sure to remember, right, it is a bit math geeky nerdy, right? There is still that sneaking problem of cycling in the background. I don't think this problem will run into that issue, right? So let's see what happens, right, if I follow the non-cycling rule for how to pick. To get rid of this 0.5, if you wanted to use a fraction, you certainly could. Remember that if you're doing fractions, a lot of times, excuse me, it freaked out a little bit because I had all the non-numbers typed in. There we go. If you're doing fractions, you might need to increase this accuracy of significant digits, or else you might get really nasty looking, there we go, really nasty looking decimals. But keeping it fractions will make things a little bit simpler. So to get rid of a 1/2, I multiply times 2. 2 times row 1 replaces row 1. And then below it, got row 2 and row 3. To get rid of that, -1/2, I need a positive 1/2 to cancel it out, plus 1/2 times row 1. And to get rid of the -1, I need a positive 1 times row 1. I'm going to click do these operations, but I don't think that 1/2 is going to cause the tool to freak out a little bit, but let's see. Okay, it's okay with that, right? I was a little bit worried that I might need to tell the computer that that 1/2 was in parentheses. I was about to go type that in. That reads a little bit clearer. I was a little bit worried that I might confuse the computer if I didn't have that 1/2 in parentheses, but it seemed to handle it just fine. Now we're at a new solution. x1 equals 10, x2 equals 0, because it went out of the basis, not a basic variable. S1 is 0, S2 is 15, Z is 20. Right? Z keeps going up. It goes up every time, if we're doing our job right anyway. But this is still not optimal. One more pivot. There's only one negative number now. So S1 is my entering variable. And I can tell just by looking, there's only going to be one positive ratio. And if you want to write all your ratios down, go for it, right? This ratio is 10 divided by -1, -10. 15 divided by +1 is +15. There's only one ratio which is positive here. That makes it a little bit easier for me. This number's already a 1, so I don't need to multiply anything. I can skip straight to the multiply and add scenario. To get rid of -1, I need a +1 times row 2. To get rid of a -2, I need a +2 times row 2. Do those things. There we go. Now let's take a look at our new solution. x1 equals 25, x2 equals 0, s1 equals 15, s2 equals 0, and z equals 50. Hey, that's not so bad. Right? And again, I know that seemed like we had to do the pivot operations 3 or 4 times. Right? Maybe if we would have chosen S2 back when we said we had a tie, maybe we would have gotten here faster. That's okay. Right? In the end of the day, I would rather do a little bit more work than have to possibly put up with that cycling issue. And it wasn't too bad, right? Once we saw how this worked, right, the pivot operations were actually really fast to do. Now you can check your work using the computer, because remember, the computer will pivot for you if you click on this button. You just need to tell it where the pivot goes. But I won't accept that as answer on the test. And so you'll need to actually show me what are the operations to move me between those pivots. And you got to be really careful, because as I was preparing for today's video, I did like a dual simplex method on a different website. And it's like, oh, wait a minute, that website's not actually giving me the correct answer. And it had lots of wonderful explanations, but in the end, oh, wait, that's not actually right. So you got to be really careful about which computers and calculators you use. I know this particular website and this particular tool seems very simple, and it is very simple. It doesn't really do the process for you. But I do know that the things that it does are accurate, or at least I haven't found any bugs to my knowledge. Okay, so this was 25, 0, and then the maximum value was 50. Normally, if we're doing word problems, we don't report the S1 and S2 values, but they are there. Like, for example, if S1 measured how much money I had, then S1 being 15 means I have $15 left over at the end. Again, not every word problem asks you to report the S values, but if you need to, you can. Okay, let's look at this new example. This is a minimize problem. Minimize z equals 2x1 plus 3x2, such that I have a less than and a greater than in this system of inequality. x1 and x2 are allowed to be greater than 0. Okay, so right away, because I have a minimize here, I know that this is going to be a dual simplex kind of problem. Because it's a minimize, I already know this is a dual simplex kind of problem. So what I'll do is I will change this to maximize. And I'll multiply everything times -1 minus 3x2. Now, when it comes to my inequalities, remember, every time I have a greater than or equal to, I need to multiply times -1. This first one doesn't need to be changed, 2x2 less than or equal to 22. But the second one does need to be multiplied times -1 to make the greater than back into a less than. And we'll fix that later. Now that I've fixed the maximize, minimize, and I've fixed the greater than, less thans, let me put this into a form that my simplex method will understand. So in the simplex method, we usually put the objective at the bottom. Now to make this back into a z, I need to move that z over to the right side. So the way the simplex method sees it, that's -2x1, minus 3x2. When I go to the matrix, I won't write the letter. Plus z equals 0. See how the easiest way to get that z being positive on one side of the equation is to move the z. In the regular simplex method, we moved all the variables to the left. Right? In this maximize, we actually move the z to the right, and that's okay. As long as all the variables are on one side, the other side is just a number. 3x1 plus 2x2 plus a slack variable equals 22. Now negative 1 x1 minus x2 plus slack variable number 2 equals negative 10. And now x1, x2, s1, and s2 must be positive. But remember, we don't usually write that explicitly, but that helps us remember what's feasible here. All of those have to be greater than or equal to 0. Z is allowed to be negative if it has to be. Change that into a simplex matrix. I'm going to go ahead and write out my variable names. I need 3 rows because I have 3 equations. And after the bar, it looks like I need 1, 2, 3, 4, 5, 6 columns. Let's bring in all of the numbers from my matrix. Remember, there are no z's, right? Or there are no s2s in that first equation. S2 is only there, not the others. And the objective function row. It's not a coincidence that we have that ones and zeros pattern there on the right side. All right, now we're at a simplex method. Now, this is a minimized process. So let's follow the dual simplex method steps here. Are we feasible? I don't think so, because x1 is 0, it's non-basic. x2 is 0, it's non-basic. s1 is 22, which is fine, that's basic. s2 is equal to negative 10, that's basic, but it's not feasible. I mean, s2 is negative 10 here. That's not allowed to be that way in my optimal solution. It's not a feasible solution here. That's all right. Z is always basic. Right now it's equal to 0. So let's do some dual simplex method sleuthing. So to step back towards feasibility, I'll pick the biggest negative number, and again, there's only one. Makes my job a lot easier, which means the pivot which I'm about to destroy is this one. My exiting is S2. I'm about to break that one. My entering depends on my ratio. My ratio here is 3. My ratio here is 2. I always pick the smallest positive ratio, which means my entering variable is x1, and my brand new pivot that's right here in this position. So when I go to the matrix of the computer, right, that will be my first pivot position. See you over in the computer. Into my new pivot, and I'm breaking this S2 pivot. Make that negative 1 into a positive 1. Multiply times negative 1. Make it a positive 1. Then, to clear out the numbers above it and below it, to cancel out positive 3, I need a minus 3 times row 2. To cancel out a negative 2, I need a positive 2 times row 2. Do that for me, please. Thank you. We are now at a new corner point, a new solution. x1 equals 10, fine. 2 equals 0. s1 equals negative 8. Still not a feasible solution. All right, and we'll keep going. We'll keep going. s2 is equal to 0. Z is equal to 20. Okay. So I've increased my Z a little bit, but I'm still not feasible. remember, I need all of these numbers to be positive before I can declare my solution to be feasible. So let's do the dual simplex pivot yet again. Here is the only negative number on the right side. This is the only thing keeping me from feasibility, which means I'm about to break this pivot. S1 is my exiting variable. Let's do some ratios to figure out what the entering variable is. -2 divided by 3, -2/3, but I'm not allowed to pivot on a negative ratio. -1 divided by -1, +1, that looks good. And here I've got a bunch of zeros. I can't pivot there, and I'm never allowed to pivot away the z either. It looked like there's only one positive ratio. It tells me that my new pivot lives in this position. My entering variable is x2. My exiting variable is s1. I need to make this into the special ones and zeros. First, I should multiply times -1 times row 1 to make that 1. Then, to clear it out, to cancel a +1, I need a -1 times row 1. I always multiply times where the pivot lives. And to cancel out a -1, I need a +1 times row 1. Do those things for me, please. Thank you. All right. Let's take a look at what my solution is now. x1 equals 2. x2 equals 8. Both of those are fine. s1 is 0. s2 is 0. They're non-basics. Z is equal to 28. Right? So z has gone up, right? Remember, we want z to be as low as possible, but all of my previous solutions were not feasible. So if my solution is not feasible in the first place, it doesn't matter how low z actually was. This was the first time that we have a feasible solution. Z is equal to 28. Well, let's look at the rest of the matrix. Can I improve upon this, or is this optimal? The optimality condition for the dual simplex method, minimizing, is I only have negative numbers here. Remember, negative numbers means z could go up. Positive numbers mean z could go down. I don't see any positive numbers here except the z, right? This one's special. You never touch the z column. The only negative numbers I see are here. There are no positive numbers, which means that this z cannot be lowered any farther. Any move I make from this position would only make z go up. And if I'm feasible, I'm allowed to box this in as my answer. Z equals 28 is the optimal solution. So x1 equals 2, x2 equals 8, s1 equals 0, s2 equals 0, z equals 28. That's the optimal solution, the minimum value of z. This is the problem, by the way, I typed into that other computer website before class, and I spent about 15 minutes going, that's not right. It's showing all of the work and all of its steps. I'm like, well, how are they setting up the problem? Am I doing something wrong? Am I doing something crazy? Stick around after the end of the video, and I'll actually show you how I eventually debugged that other computer website, and I verified for myself that my solution had to be correct. Stick around after class now, and I'll show you how I did that. All right, last example. One last problem. This one has more variables in it, though. This one has x1, x2, and x3, as well as 3 different inequalities. Again, I'm not writing the requirements. All of my variables must be positive, although it's always there. Let's change this into a simplex method matrix. I don't need to change this from a minimize to a maximize. It's already a maximize. But I do need to change a couple of greater thans into less thans. So I will do that now. Minus 4x1 minus x2 less than or equal to -10. I'm multiplying everything times -1. I don't need to do this for the second inequality. 3x3 less than or equal to 30. But I do need to do it for the third. Okay. And just to make that look a little bit more like a matrix, I'll go ahead and move this over a little bit. There we go. And so now, this is my set of inequalities. Now let's turn this into a simplex ready sum of equations. I'll start with top inequalities, add a slack variable. I add the slack variable, becomes an equal sign. Do the same thing in inequality number 2. I'll go ahead and I'll move over that slack variable. That way we can kind of see the matrix forming. Do it for the third inequality. Oh, leave it to me to copy down the wrong one. Add a third slack variable. And now my objective function, when I get that p moved over, actually it looks like I should move all the variables to the left, right, so that p remains positive. Minus x1 minus x3 plus p, 0. Right? Basically, the variables are going to be negative either way, right? Because if it's a minimized, we've already multiplied by a negative, but we move p to the other side. So my simplex method looks like this. Got x1, x2, x3, s1, s2, s3, p, and across the bar. Pretty big matrix, but that's okay. I'm just going to copy down all the coefficients. Remember, wherever those variables are not present, I have a 0. So in this case, there's a 0 in the x3 column and in the s2, s3, and p column. 1, 1, 3, 0, 30, negative 2, 1, negative 1, negative 4. You kind of see how the right side of this matrix forms that zeros and ones pattern. It should. Right? If you've done everything correctly, it should. But I still like to make sure that everything I've written above points to that. Okay, this looks good now. It's a bigger matrix, but that's okay. My calculator tools will help me do this matrix very quickly in the computer. Let's take this back over to the computer now and work on it. Okay, got it all typed into the computer and we're ready to go. This is a maximization problem, remember, so we're following sort of the primal optimization techniques, but I've still got negative numbers over here in the right side, which means that I'm not feasible right now. Remember, x1 is 0, x2 is 0, s3 is 0, s1 is negative 10, s2 is 30, s3 is negative 15, p is 0. So I need to take some dual pivot operations to get back to feasibility before I can worry about optimality. The negative number, which is biggest, which tells me I'm farthest away from feasibility, lives here in the third row. Which means that's the S3 pivot. I'm about to break it out. That's the exiting variable. Let me do the ratios to figure what comes in. So that's negative 1 divided by negative 4. The negatives cancel. Can't pivot with a 0. Negative 1 divided by negative 2. The negatives cancel. So the lowest ratio is here. My entering variable is x3. My exiting is s3. I need to pivot in this location here. Let's do some row operations to make that happen. To make that a positive 1, I'll do negative 1 over 4 times row 3. That's another way you can see the fractions, by the way, using a space. Why did it do that? Extra numbers here. Excuse me. I think it's because I typed something in and I didn't delete everything. Excuse me. So got a 1. So I'll use that row 2, row 2 and row 4 need to change. To cancel out 3, I need a negative 3, row 3. Cancel out the negative 1, I need a positive 1, row 3. Do those things for me, please. All right. New solution. X1 is 0, X2 is 0, X3 is 4, S1 is negative 10. Still not feasible yet. S2 is 18, S3 is 0, P is 4. Okay, still got a negative number. So I need to do is go to the dual simplex method pivot. This is the only negative indicator on the right side. I'm farthest away from feasibility here. So S1 is my exiting variable. Let's do the ratios to figure out the entering variable. Can't pivot here. Can't pivot divided by 0. That's going to be a negative number. 1/4 divided by negative 1. Negative 1 over 4. Right? Normally I would just skip it because I can't pivot on a negative ratio. Negative 1/2 divided by negative 4 plus 8. Okay, so I know where I'm going to pivot at. Right here. So my entering is X1. My exiting is S1. Right? That's the pivot I'm about to mess up. To make that negative 4 into a positive 1, I need a negative 1 over 4. And then to make all the rest of these rows 0, 2 changes, row 3 changes, row 4 changes. Cancel out a positive, or I need a positive 1/2 to cancel a negative 1/2. I need a negative 1/2 to cancel a positive 1/2. And I need a positive 1/2. Excuse me, I need a positive 1/2 to cancel out negative 1/2. Excellent. Special 1s and 0s. New solution. X1 is 5/2. X2 is 0. X3 is 11/4. S1 is 0. S2 is 77 over 4. Right? S3 is 0. P is 21 over 4. Now I've got a feasible solution. There are no more negative numbers on the right side. So now I can turn my eye towards optimality. If I'm maximizing, then optimality means there are no negative numbers in the bottom row. Negative numbers in the bottom row means Z could go up or whatever. It looks like I have a P here instead of a Z. Your excuse me. Your objective function can go up. I had a senior moment there. I'm not that old. Don't send anybody. If I look at the negative numbers, I pick the biggest negative number. Negative 1 over 4 is bigger than negative 1 over 8. We do the ratio. Normally I would say don't bother because the only positive ratio is going to be here. 11 over 4 divided by negative 1 over 4 is negative 11. 77 over 4 divided by 3 over 4 is 210, 231. Right? I'll let you use your calculator. But normally I would look at this and say the only positive ratio is here. I don't actually need to do the division. So that means my entering variable is S3. My exiting variable is S2, right next to it. Sorry, S2, I know we just brought you into this thing not that long ago, but we have to kick you out. To make this into a 1, I need to use the reciprocal fraction, 4/3 times row 2. Now, row 1 does not need to change. There's already a 0 up there. But row 3 and row 4 do need to change. Cancel out a 1/4 or negative 1/4. I'll need a positive. Cancel out a negative 1/4. I'll need a positive 2. Do these things. Thank you. Notice how we're still feasible because I still have positive numbers here. X1 is 5/2. X2 is 0. X3 is 55/6. S1 is 0. S2 is 0. S3 is 77/3. Are we optimal? Not yet. And I still see a negative number down here in the bottom. So we need to do yet one more simplex method pivot. Hopefully just one though, because I only see one negative number here. Let me do the ratio. I might actually have to get out my calculator for this. 55/6 divided by 1/12. That's actually 110. The ratio is 110. Here, 77/3 divided by negative 1/6. I'm not even going to bother to write that down because it's negative. 5/2 divided by negative 1/4. I'm not even going to bother to write that down because it's negative. It looks like the only positive ratio is here, which tells me this is where my pivot should be. That tells me my entering variable is S1. My exiting variable is X3. Man, it just seems like we're shuffling all of these around. Right? I brought them in and now I'm kick them back out. Okay. To get rid of a 12/1, I multiply, or to get rid of a 1/12, I multiply times 12/1. And yes, I know that I could have just said 12. So row 1 needs to change, row 2 needs to change, row 4 needs to change. Cancel out a negative 1/4, I need a positive 1/4. Cancel out a negative 1/6, I need a positive 1/6. And to cancel out a negative 1/6, I need a positive 6. Do those things for me. Excellent. It looks like we got back to whole number solutions, and that's okay. You know, sometimes the simplex method is a little trickster like that, and it brings you through all these fraction nasties, and then in the very end, it dumps you right back onto a whole number. Let's take a look at this solution. X1 equals 30. X2 equals 0. X3 equals 0. S1 equals 110. S2 is 0. S3 is 44. P is equal to 30. After all of that, the maximum value of P is equal to 30 at 30, 0, 0. Again, you don't usually report your S variables, but if you had to, S1 would be 110, S2 would be 0, S3 would be 40. Excellent. And so that was probably the longest, hardest simplex method I could think of. Right? It combined a little bit of everything, a little bit of maximize, a little bit of dual simplex, a little bit of the weird negative numbers coming into play. Right? This is about as crazy as we could make it. Right? And the nice part about this is that once you learn how to read the matrix, right? You remember the movie The Matrix, right? Was the character's name Tank. He was looking at the screen and all he was seeing was the numbers that were scrolling by. But he could read the numbers. He knew how to interpret those numbers to make meaning out of them. That's kind of what we've done during this unit. Right? We've taken matrices and we've learned how to read them. We've learned how to surf through all the corner points to find the one which is optimal, or at least know when to read in the matrix to tell us when it's not optimal and move towards that optimal solution. There's a lot going on in this section, and we're just about done. After this unit, the test this week, next week we'll be back on solid ground when it comes to probability. You'll find that one a lot more simple to do. Right? The calculations are a lot simpler, but again, I think there's more concepts. Right? Once you learn how to read the matrices, these concepts are actually really easy. And you've probably been coasting by for maybe a week going, oh man, right? We're just doing this matrix stuff again. Right? But now that we're back into Unit 4 next week, right, it'll be back to, I've got to get all these definitions in a row again. Right? So I promise that it will be a little bit easier, at least to take tests and to take assignments next week, because it will be back in my open math for the most part. Until then, I'll see you. Have a good one. Okay, bonus time. Right? So how did I decide that this solution for my example number 2 was the optimum solution and all the other ones were just were crazy? Okay? When it comes to finding your pivots, remember, there have to be 2 basic variables and 2 non-basic variables among this set of variables. So here's what I did. I basically, right now the 2 basics are here. So all I'm going to do is swap them out. Right? So let me take the one in the top row and move it here. Rather than show you all the arithmetic that goes into that, I'm just going to click the pivot on selection button. And you see how now my 2 basic variables are here, x1 and s1? Well, this solution is not feasible. We saw that one as part of the process. Okay, move the second pivot here. So now my pivots are x1 and s2. This solution is still not feasible. Right? So I've already exhausted all the situations where x1 is one of the pivots. Now let me move this one over to x2. Move this back to s1. You see, I'm just kind of going one at a time. And I come back and I go one at a time. Right? You can do this for any simplex method problem, but usually this would take you far too long to do. Right? With this calculator tool, it helps to go faster. But what I'm essentially doing when I'm just paging through all the different corner points like this is I'm basically doing the method of corners. Remember way back on exam 2 when we made a list of all the corner points? That's basically what I'm doing, but with a simplex method here, or with a simplex matrix here. When x2 and s1 are, when x2 and s1 are basic variables, then my z value is 30. Right? It's feasible, but the z value is 30. Right? Remember, my optimum z value was lower than that, and I'm trying to minimize here. And so I know that something was up, and I can see here that because there's a positive number in the bottom, I know that my z value could be lower. But let's keep going. Remember, I'm basically doing the method of corners right now. Pivot here. This one is feasible, but my z is even higher now, 33. I've got 2 positive numbers in the bottom, so I know that something is wrong here. The only thing left to do is here at the end, S1 and S2. That's kind of where we began. I know that S1 and S2 were the other way around, right? S1 was in the top, S2 was in the middle. But I began this process with S1 and S2 being basic variables. And just like I saw then, I'm not feasible. I've got a negative number, and my z was 0. So I basically did the method of corners using the simplex matrix. And it's a neat trick, and that's how I verified for myself that the other website I was using had to be wrong, right? It came up with a different optimum solution. It came up with 28 as its optimal value of z, so it was correct there, but it did not come up with the correct values of x1 and x2, and it confused me for about 15 minutes. And so be very careful when you're using other websites and other calculators. Make sure you know what you're doing. That way they don't lead you astray. I'll see you next time.